Hi everyone. In this video, we are going to start chapter 6, which is all about quantities in chemical reactions. So in chemistry, there is a way to convert the mass of one substance into the mass of another substance. And this is really useful. So for example, let's say we're in lab and we measure out a certain amount of reactant, and we want to predict how much product we expect to form. So we can very easily do that. Unfortunately, there isn't a direct way to calculate grams of one substance from grams of another substance. We do have to go through a quantity called the mole. So off to the side, there's a chart showing how we do those calculations. So if we're given grams of, let's say, our reactant, substance A, we can predict how many grams of our product would form, and let's call that substance B. So again, we have to go through this quantity called moles first. So we would convert grams of A to moles of A, and then convert moles of A to moles of B, and then we can finally get to grams of substance B. So we'll learn how to do this today, and this will come in very handy in future labs. Now first, let's talk about what a mole actually is. So this is a unit of measurement, just like anything else that we've been using. It's a very specific type of unit though. It's really similar to 1 dozen. So if we tell somebody to pick up a dozen eggs at the store, we know that they mean pick up 12 eggs at the store. And the same goes for a mole. A mole is equal to a very specific amount of something. So a mole is understood to be 6.022 times 10 to the 23rd units. So we could replace units with whatever we're counting. So for example, if we told somebody to pick up a mole of eggs at the store, we would be telling them to pick up 6.022 times 10 to the 23rd eggs, which is way too many eggs. So why such a big number? Well, in chemistry, we're usually talking about very, very tiny particles, right? We're talking about atoms or molecules or ions, and we need this really large number to accurately tell somebody how much we have. So in a typical sample, we do have many, many atoms or a lot of molecules, so we do need this big number. Now down below I have a figure showing 1 mole amounts of different substances. So for example, we have 1 mole of mercury 2 oxide. We have 1 mole of sucrose, sulfur, copper 2 sulfate pentahydrate, sodium chloride, and copper. Now, even though each of these samples contain 1 mole, so they contain 6.022 times 10 to the 23rd molecules or atoms, whatever it is, they do look very different, right? It looks like we have a smaller amount of copper compared to sucrose, for example. But there's actually the same amount if we were to actually go in and count how many of each we have. So we do have the same amount of sucrose and copper, but they're going to weigh different amounts, and that's why they look different. So this would be the same as, let's say we had a dozen textbooks. So 1 dozen textbooks. And we compared that to 1 dozen marbles. So 1 dozen marbles is going to look a lot smaller than 1 dozen textbooks. So 12 marbles versus 12 textbooks. So they are going to weigh different amounts in grams, but if we count them, we have the same number of textbooks and marbles. So it's the same thing going on here with our molecules and atoms. Sucrose is actually composed of multiple carbons, hydrogens, oxygens. So one molecule of sucrose contains a lot of atoms, whereas copper is just one atom. So that's why they're going to look like we have different amounts, but we actually have the same amount. Now, this number that we've been referring to is also called Avogadro's number. And this is named after the 19th century chemist Amedeo Avogadro. Now, the units that we talked about before, those can be atoms, molecules, ions, or really anything that we're counting. So down below I have some examples where 1 mole of sodium atoms is equal to Avogadro's number of sodium atoms, and 1 mole of water molecules, H2O, is equal to Avogadro's number of water molecules. And then we have 1 mole of sodium ions, and that's equal to Avogadro's number of sodium ions. So again, if we tell somebody I have 1 mole of something, that means we have Avogadro's number of that item. So we can use that equality of 1 mole is equal to Avogadro's number of units as a conversion factor. So we can use the mole relationship and a chemical formula to convert back and forth between moles and number of chemical entities. So let's start simple. Let's just do an example together and figure out how many moles are equivalent to 1.81 times 10 to the 24th molecules of N2. Okay, so we have our equality down below. And let's figure out what we're solving for and what we're given, because that will help us set up our dimensional analysis. So it looks like we're being asked to solve for moles. And we're given 1.8 times 10 to the 24th molecules. So when I'm setting up a problem like this, I always start with what I'm given. So let's write down 1.81 times 10 to the 24th molecules of N2. And next, I'm going to set up my conversion factor. You could also use those railroad tracks if you're used to that. It's the same thing, just kind of drawing it differently. Now on the top of this line, I'm going to put what I'm solving for. So in this case, that will be 1 mole. And that is on the left side of our equality here. And that will be 1 mole of N2. And then in the denominator, I'm going to use, actually let me use green, the other side of this equality, which is Avogadro's number. And we can use any unit that we want after Avogadro's number, and in this case, this will be molecules of N2. So let me actually extend my line here for my conversion factor. We're running out of room. So let's make sure that our units cancel appropriately. So molecules of N2 will cancel and we'll be left with moles of N2. Perfect. All right, so now we can calculate the answer. So it looks like if we simplify the numbers, this is 1.81 times 10 to the 24th divided by 6.022 times 10 to the 23rd. Now, when you plug this into your calculator, I highly recommend using parentheses around the number in the denominator because sometimes your calculator can get confused and assume that you're actually multiplying everything by 10 to the 23rd. So in order to make sure you're actually dividing by Avogadro's entire number, put parentheses around it, and that will help a lot, especially on tests or quizzes. You don't want to get that wrong. Okay, so if we plug this into our calculator, I'm actually going to do this off to the side as well. So 1.81 times 10 to the 24th divided by Avogadro's number, that gives us 3. And remember, our unit is moles of nitrogen. So if we have 1.81 times 10 to the 24th molecules of nitrogen, that's equivalent to 3 moles of nitrogen. All right. So this is a handy way to also count how much of something you have, because again, there isn't a good way to count all of the molecules you might have in a sample. That would take forever, especially since they're really small molecules. Now let's do another example. So let's say we have the molecule ethanol. This is alcohol that's found in alcoholic beverages. It's also found in gasoline. You might notice at the gas tank it says, the certain percentage of ethanol that's in the gasoline. But ethanol has the molecular formula C2H6O. Now we want to figure out in the first part how many molecules of ethanol are equivalent to 1 mole of ethanol. All right, so this one should hopefully be pretty easy, right? So let's figure out what we're given and what we're solving for. So it looks like we're solving for molecules of ethanol. So that's what we want at the end. And we're given that we have 1 mole of ethanol. So I'm going to start with what I'm given, 1 mole of C2H6O, which is the formula for ethanol. And then we're going to multiply that by our conversion factor. So again, we want to put what we're solving for in the top. Now in this case, we want to solve for molecules of ethanol. Now looking up above, we have our conversion factor again. So this time we want to use the right-hand side of our equality because that's going to allow us to count how many molecules of ethanol we have. So I'm going to write 6.022 times 10 to the 23rd. And remember, we can use any unit, so whatever we're counting can go after Avogadro's number. So I'm going to use molecules of C2H6O. And then in the denominator, I'm going to put the other side of my equality, which is 1 mole of C2H6O. So this should be pretty easy. We're just canceling 1 mole of ethanol in the numerator and the denominator. And this should equal Avogadro's number of molecules. Let's see. So I ran out of room, so I'll put this up above. I should have given myself some more space. So the answer will just be 6.022 times 10 to the 23rd molecules of C2H6O. Super easy, right? We didn't even really need to set up dimensional analysis for that one. We could have just known that 1 mole of something is equal to Avogadro's number. But it's always good to get practice with dimensional analysis. So now let's look at the next question. How many atoms of hydrogen are in 1 mole of ethanol? Okay, so let's focus on what we're given and what we're solving for. So it looks like we're asked about atoms of hydrogen. So that's what we're solving for. And then we're told that we're given 1 mole of ethanol. Okay, so to figure out atoms of hydrogen, we need to figure out how many hydrogens are in ethanol. So let's look at C2H6O. And we can figure out how many hydrogens there are in ethanol by looking at the subscripts. So it looks like there are 6 H atoms in C2H6O. Okay, but that's not really telling us the whole story, right? Because we want to figure out how many hydrogen atoms are in 1 mole of ethanol. Now, in 1 mole of ethanol, we already know that we have 6.022 times 10 to the 23rd molecules. So let's start there. So that's equal to 1 mole of ethanol. And then we're going to multiply that by 6 H atoms that are in 1 molecule of C2H6O. So we're really just looking at the ratios or the subscripts in our formula to figure out this answer. All right, so let's make sure our units cancel. So molecules of C2H6O cancel. And all we're doing here is multiplying Avogadro's number by 6 to figure out the total amount of hydrogen atoms in our sample. All right, so this would equal, let's see, let me plug this into my calculator. So Avogadro's number, and then we're multiplying that by 6. So that should give us 3.613 times 10 to the 24th atoms of hydrogen, or hydrogen atoms, whichever way you want to write that. Okay, so if you can picture, let's say we have just a sample of ethanol, which is a liquid, and we know that we have 1 mole of ethanol, but there isn't a good way to zoom in on the sample and count all of the molecules of ethanol, right? However, we do know that 1 mole of ethanol is equal to Avogadro's number of molecules of ethanol. And then let's say that we're curious, okay, I know each molecule of ethanol has 6 hydrogens. So how many total hydrogens do I have in that sample? And that's where we can just multiply Avogadro's number by 6. And that will give us the total amount of hydrogen atoms in that sample of ethanol. Now, it is tough to visualize these things in chemistry in particular because, again, there isn't a good way to zoom in and actually look at these molecules, right? All right, so let's do one more practice problem. I'll let you try this one on your own. So this question asks, how many molecules of water are equivalent to 2.4 moles of water? So figure out what you're given, what you're solving for, and then set up your dimensional analysis to solve for the water molecules. So pause the video, try it on your own, and then we'll try it together. All right, so let's figure out what we're given and what we're solving for. So it looks like we're asked about molecules of water, so that is what we're solving for. And then we're given 2.4 moles of water. So remember, we're going to start with what we're given. And if you want, you can also abbreviate moles as MOL. You cannot do that for molecules, however. Molecules has to stay the full word, but you can abbreviate moles as MOL. It's kind of silly because molecule is a bigger word, but all right. So now we're going to set up our conversion factor. Now we do have our equality up above that we can use as a conversion factor. And since we're trying to count how many molecules we have, let's use the right side of that equality in the numerator, because that's what we're going to solve for. And remember, our unit can be whatever we're counting. So in this case, that will be molecules of H2O. And I'll just extend my line here. And then we'll cancel moles. So we'll put that in the denominator. So 1 mole of H2O. All right, so moles of H2O will cancel in the numerator and the denominator. And then if we simplify what's left in terms of the numbers, we have 2.4 times 6.022 times 10 to the 23rd. And we get our desired unit, which is molecules of H2O. Okay, so let's figure this out. I'm just going to multiply Avogadro's number by 2.4. And we should get 1.4 times 10 to the 24th molecules of H2O. So that's how many molecules of H2O are in 2.4 moles of H2O. All right, so again, Avogadro's number is just a way that we can count really tiny units or atoms, molecules, ions, because again, it would take forever to count all of those molecules or ions. And in some cases, it would be way too difficult. For example, if we had a gas or a liquid. So this is a way that we can figure that number out. All right, so in the next video, we're going to learn about molar mass, and this will allow us to convert between moles and mass. So I will see you then.